All right, so let's get this started. Uh, since we didn't have class on Thursday, I actually did make a class video covering 9.3 and 9.4. And since I know that everyone totally watched the video, right? Absolutely. And you're clearly going to have a couple questions on it, some of the things we did in there. I am going to do a couple practice problems from that. Uh, Today we've got 9.5 and 9.6. On Thursday we've got 9.8, and then we have some time to review for test number 3. So test 3 is going to be next Tuesday. Just had to look it up. The final exam is going to be on uh, whatever the normal Tuesday is going to be. So 4/29. Class period or the final exam is going to be same on Tuesday, same time period that you're used to, since these videos are going to be for the earlier class as well as you guys. I'm not going to mention what the hours are, but for you guys, since you're the later one, if you want to come in 20 minutes early to have some extra time on that, it's like get in at 10, totally fine with that. For my earlier students, if they want to stay 20 minutes beyond their class period, I've got no problem with that. I'll try to keep all of you equal. But for all of you in here, we do need to be out of here at like 12:20 because we've got the other class coming in. A lot of the material that we're going to be covering today. So you can see it says solve applications of quadratic equations. When you look at the applications that they're using, I think the only thing I could say about those were really, you call that an application? Ugh. So anyway, couple of the big things that came out with the class video. One, if you do watch it, what have I been telling you guys about or telling you all about quadratics and stuff like that? Graph it, then math it. If you watch the video, I'm actually graphed one of the equations. We saw what the answer was supposed to be. I went to math it. I actually wrote down the wrong -6 instead of +6. Still came up with a really nice answer that if any of you were doing it, you would have looked at it and went, yeah, that looks like a happy answer. That looks reasonable, but it would have been wrong. So then spent like 15, 20 minutes trying to figure out where I went wrong and then realized it and then went back and corrected it. Uh, since I made that mistake, and we weren't in class. I've already put it in for all of you. I still have to do it for the earlier class, but everyone's getting the in-class credit for that plus 2 points of extra credit because I did screw up and screwed up bigly. So graph it, then math it. And as long as you can graph it, then math it, pretty much everything we're going to be doing in these 2 sections, so much easier. All right. So to talk or to because there were a couple things that came up in the last class video that we need to discuss. Some of the problems that were in there were like x to the -4 plus, say, 5, x to the -2 plus 6 equals 0. Part of the idea with a problem like this is one, we have something that is in a what's called a quadratic form, but does that look like a quadratic equation that we've ever used? Absolutely not. Plus, it's got negative exponents, which means it's going to be fractions. And I know how all of you just absolutely love fractions, right? So this is actually kind of like a 2-4. What we end up doing with a problem like this is we have to use something called substitution. Most of the time when we're doing substitutions like this, we use U. So if you try to look up videos on like YouTube or something like that, if you look up U substitutions, quadratics, this is basically what's going to be going on here. And what we have is we're going to say x equals -2. We're going to say U squared equals x to the -2 squared, which, as you all totally remember and totally love to death, it's going to give you x to the -4. Once we've got that, we can plug in our substitutions here. So we'll have U squared plus 5U plus 6 equals 0. For U squared plus 5U plus 6, if you see what it's going to factor out to be instantly, awesome. If you don't, I'll actually show you a function that's on some of the calculators, how you can figure this out without actually having to go through and do the calculation. It's not on all of them, but it should be on most of them. So when we factor this, we're going to have U plus 2, U plus 3 equals 0. And what's going to happen is we are going to say U plus 2 equals 0, then U plus 3 equals 0. We're solving for U, so this is going to give us U equals -2. This is going to give us U equals -3. But the next step here is where it gets a little bit awkward. Because we use the substitution U equals x to the -2, we actually have to replace and back substitute here. So x to the -2 equals -2. X to the -2 equals -3. As a reminder, when you have a negative here, we get 1 over x squared equals -2, and 1 over x squared equals -3. We're still trying to figure out what are the values of x that we're going to get. And when we look at this original equation here, it says -4, so that's actually 1 over x to the 4th. That's telling us that we're going to have potentially four different answers for x. Some of them might be duplicates. Some of them might not be. Looking at the values we've got down here, I can tell you they're not going to be. So now I've got 1 over x squared equals -2. What's my next step here going to be? I need to figure out what x is. So how do I go from 1 over x squared equals -2? How do I get x in the numerator? We've got fractions. Do we like fractions? Do we ever like fractions? How do we get rid of fractions? Multiply by the denominator. In this case, we can make this do this in one step. And just basically flip these around. That's going to give us 1 over -2 equals x squared, and 1 over -3 equals x squared. Now I've got x squared. I need x. What's my next step going to be here? I unsquare, right? What's that called? square root. So square root of both sides. And we have to remember when you take the square root, you're going to have plus and minus whatever that happens to be. So with all of this, eventually we get x equals plus and minus the square root. I said 1 over -2, but we can write that as -1/2. And over here, we can also say that it's plus and minus the square root of -1/3. Because we've got the negatives and because we're taking an even root, that means we're going to have complex numbers here. So square root 1/2, and then outside of the root somewhere, we're going to have an I. So you could write it like that, or you might even want to bring the I out in front just to make it a lot more obvious what we're dealing with here. So we've got plus I times the square root of 1/2 minus I times the square root of 1/2 plus I times the square root of 1/3 minus I square root of 1/3. And then you look at all of that and you're like, okay, that's a thing. It just happened, right? What if you were to put those answers into your online homework and those are the correct answers, do you think the online homework is going to give you full credit for what you just put in there? Because remember, with these, we can rewrite them. So square root of 1 over square root of 3. Square root of 1 is 1. So that's 1 over root 2 and 1 over root 3. How does the book feel about having radicals in the denominator? What's our next step going to be here? We've got to get the radical out of the denominator. So this will be plus and minus I 1 over root 2. And then we multiply denominator and numerator by square root of 2. So this becomes plus and minus I root 2 over 2. Multiplying numerator and denominator here by square root of 3. Using the same process, we get plus and minus I square root of 3 divided by 3. Final answer. So in this one problem we used what? 5 or 6 different sections worth of the material to answer one silly problem. So these are the types of things that we need to be aware of. There are other types of problems that we can come across as well. So if we have something like, say, x to the 6 plus 5x cubed plus 6 equals 0. We can use the same idea of a substitution. So we're going to have u equals x cubed, u squared will be x cubed squared, which is going to be that x to the 6. Plug it in, we get the same thing we had before. So we already know that u is going to come out to be what? -2, and u It's going to come out to be a -3 once we solve everything. Problem is here, we now need to realize x cubed is equal to -2, and x cubed is equal to -3. So if I've got x cubed, how do I uncube it? What do I have to do here? It's the cube root, right? So we get x equals the cubed root of -2, and x equals the cubed root of -3. Looks like way too much fun, doesn't it? So move that over here for a moment. And that, of course, is just going to give you one of the roots that comes out of there. The rest of it, you have to use the equation that you had on exam number 2, where you have like a cubed minus b cubed, or a cubed plus b cubed. And you go that extra step to get the 4 other values of x on there. Oops, didn't want to do that. Wanted to do that. So 9.5 is solve applications of quadratic equations. When you look at a bunch of the alleged applications that are in here, they're all the kind where you can tell that a mathematician looked at it and went, oh, here's a neat little trick. With some of these here, depending on what your, say, Facebook or Twitter or whatever feed is filled with, they'll have a whole bunch of questions on there, like, can you name 2 consecutive integers, or can you name 2 consecutive, and here it says odd integers, that when you, so it says down here, the product of 2 consecutive odd integers is 195. Well, how do we figure that out? The product basically means we're multiplying 2 consecutive odd integers. That's telling us that we have n, which is going to be one of these values. We don't know what the other value is, but we know that it's going to be 2 more because we said 2 odd integers. If we said 2 even integers, that's equal to, say, 100 or something like that. Well, we'd do the same thing if we said it was 2 consecutive integers. So like 2 consecutive integers equals 56. We'd have n times n plus 1 because we're looking at 2 consecutive integers. You can see how they translate that into the equation. Bring 195 to the other side, factor that. You can see here that they've got 2 different answers here. So when you plug those in, you have to see, does 13 and 15, does that actually make the original equation correct? And then we can look at -15 and -13, does that make the initial equation correct? So in this case, as long as both pairs work, we've got 2 different answers that we could actually go with here. So that is something we need to be aware of. So dealing with what we've got there, it says the product of two consecutive odd integers is 99. So the product of two consecutive odd integers. So again, we're going to call it x or n and n plus 2. That's going to be 99. Distribute the n. So n squared plus 2n equals 99. N squared plus 2n minus 99 equals 0. And we now get to factor that equation. If you see what you can get with that instantly, awesome. If you don't, is that much of an issue? You can use the quadratic formula. And since you all totally know how to use the quadratic formula by now, right? You can just take this and say n equals negative b plus and minus square root b squared minus 4ac divided by 2a. You know that a is 1, b is 2, c is negative 99. So you get negative 2 plus and minus negative, or sorry, that should be a 2 squared minus 4 times a times c divided by 2a. Plug all that in, you can do the math. So at that point, you could do what with this problem? Graph it, see where the numbers come out, and then be like, yeah. See, when I did all that, this is the answer that I got. But as you know by now, you're not necessarily going to get the everything that, or you're not going to necessarily get integers. Sometimes you're going to get some funny stuff like -1 plus and minus 2 times the square root of 5 divided by 3 or whatever. So one of the things you can do if you have a calculator that has this on it, you can go to apps. You can arrow down to where it says please Smult2. I have no idea what please Smult2 stands for. But you can go to please Smult2 and simultaneous equation solver or polynomial root finder. Because we are dealing with polynomial equation, specifically a quadratic, that we want the first thing. The simultaneous equation solver, that's like problem 1 on exam 2, where you've got 3 equations, 3 unknowns, solve for x, y, and z. We're doing polynomial root finder. What's nice about this is you can go up to x to the 10. So I can give you an extremely horrific equation and tell you, yeah, find the or factor this. You plug it in here. So if I gave you like we were doing the problem x to the 6, oops. So if I want to do that problem that we were just working on, where it's x to the 6 plus 5x cubed plus 6 equals 0, I can pull that over to 6. You can see that it's automatically doing complex roots, because most of the time that's what's going to happen. When you look on here, it says next. That corresponds to the graph. Help corresponds to trace. Main corresponds to y equals. So I want to hit next. And in this case, a to the 6, what's the coefficient? It's 1. A to the 5th is 0, a to the 4th is 0, a to the 3rd is 5, a to the 2nd, a to the 1st are 0, a to the 0 is 6. Now again here, main corresponds to y equals, mode corresponds to window, clear corresponds to zoom, load corresponds to trace, solve corresponds to graph. And there are the answers. And it's clear as day that those are the answers, right? And when you look at these, so even if I try to make the graph even bigger, or where we have those answers even bigger, it's not actually doing it. Basically, these first two here are when you go in and you solve that solve that equation originally. So this is going to be like cubed root of -2, cubed root of -3. Those are the real answers. When you look at all of this stuff here, everything on this side, that's going to be a complex root. So there's going to be an I involved with it. So if this was, say, a problem on the homework or on the exam, say like cubed root of 2, cubed root of 3, 0.721 plus 1.25 I, 0.721 minus 1.25 I, 0.63 plus 1.1 I, 0.63 minus 1.1 I. There should also be an ability. So if I go to the main thing, it's automatically giving you everything in decimals here. So it's not giving you a chance to look at decimals versus fractions. But you can at least get an idea of what the answers are going to be, know that there are going to be a couple complex answers in that solution. So trying to solve the new equation that we have here, which is n squared plus 2n minus 99. We want order of 2, automatic, normal, float, degree. So I have to hit graph. And on this calculator, it now looks like this. On one of the other calculators I was using, it looks like the other thing that we had, where we had A6, A5, A4, A3, and all that. So I can now say the thing out in front of n squared is 1 plus 2, and then that's going to be minus, and then that's going to be 99. And again, we want to solve this, so I have to hit the graph button. Answers, right? So same type of problem that was in the textbook. If you have 9, what's another consecutive odd value from 9? 7 and then 9 are consecutive and odd, right? 9 and 11 are consecutive and odd, right? So 9 times 11, does that give you 99? Which is what this is telling us here. If we have -11 times negative 11 plus 2. Negative 11 plus 2 is negative 9. Negative 11 times negative 9, does that also give you 99? How many of you wish you knew how to do that on the last exam? So one of the weird things, if you need to get out of here, you have to hit second and then quit. Sometimes you have to do that a couple of times. If you just hit clear and keep hitting clear, that's not necessarily going to clear it out. If you turn the calculator off and then turn it back on again, that might clear it out. Might clear it out. So when we're yeah, when we're looking at some of these, it's the same thing over and over again. So it says here, an architect is designing an entryway of a restaurant. She wants to put a triangular window above the doorway due to energy restrictions. The window can only have an area of 120 square feet. The architect wants the base to be 4 feet more than twice the height. Find the base and the height of the triangle. So we've got the height of the triangle, and then the base of the triangle is 4 feet more than twice the height. We have to know that the area of a triangle is 1/2 times BH. We know that B is going to be 4 inches more than twice the height. Plug everything in, factor it. And then what's looking at this, what we have to do is try to rationalize the two values we get. Can you have negative distance if you're talking about glass? No. So we can eliminate the negative value here to give us the positive value. And there are a couple of other problems that are like that on here. Does anyone actually care about trying to figure out the distance or what is it, the height of a flagpole based on the length of the shadow a flagpole casts and blah blah blah? Probably not. So an actual useful application for this stuff, since it is baseball season. I'm gonna assume that we've all seen at least a baseball game before. If you're not a baseball fan, tough, because at least this is something that might actually be useful. Uh, if you watch a lot of baseball games and someone hits a home run, what's one of the metrics that they usually talk about with that home run? It's basically how far did it travel, right? So one of the ways that you can actually calculate all of that is, suppose for a moment, so that's the backstop. That's the entire field. Let's say out here, this is going to be, or the fence is going to be, say, 350 feet away. And there are going to be some stands that come up like that. And right about there is going to be home plate. So the distance from here to here is going to be that 350 feet. When the pitcher throws the ball in, that ball is going to be at a certain height above the plate. Depending on the person at the plate, the height of that ball could be anywhere from, say, 1 to 3 feet. So I'm going to say it's at X point 0, but it's also going to be 3 feet above the plate. When the player hits that ball, travels up, hits a certain point, and then it starts to come down. And let's say that we know that the high point here, or as we're going to get into later at the vertex here. We know that this happened at, say, 220 feet. So from here to here is 220 feet. And the height of the ball, I don't know, let's say it's 130 feet. And we know where it hit in the stands here. Since this is 350, let's say it hit 380 feet. And it was also, say, 30 feet up. Does that make sense? Now, when you watch the baseball games, they're actually going to be talking about what? How far did the ball travel? Well, because of the stands, it only traveled 380 feet. But when they give you that number, what they're talking about is essentially what is the projected distance if it had been nothing but flat land. So even though we know for a fact that it went 380 feet, we also know that it could have gone even further. But the question is how much further? Based on the data that I've just given us here, we can go to our graphing calculator. We can go to stat, and then we can go to edit, and we can clear this stuff out of here. I'm going to call L1 our X values, and I'm going to call L2 our Y values. So our first X value is 0. Our second LX value is 220. Our third X value is 380. Our first Y value started 2 feet above the plate. It went a total height of 130 feet. And then when it landed, it was 30 feet above the ground. I can take those 3 data points. I go to stat, over to calc, down to quad reg. X list is L1, Y list is L2. Just keep mashing the enter button or the down arrow till I get to calculate. And we just came up with an equation for determining the trajectory that the baseball traveled. So we know that it's now y equals negative 0.00318 x squared plus 1.28x plus 2. Now, one of the things that we're going to get to is if you look at the coefficient for this x squared term here, in this case it's negative, that's letting us know that this opens downward. If this value happens to be positive, we know that it's going to open upward, so it's like a smiley face. Once we've got that equation, we can factor it, and we're going to get a couple values of x. So one of the values is going to be negative. The other value is actually going to be positive. This negative value is basically how far behind home plate the ball would have traveled if it was going in the opposite direction. The positive value gives us the distance it would have traveled. Since we now have that particular equation, we can go back to apps, go down to please Molt 2. We want to do the polynomial root finder. Click on next. This is going to be negate point 0.00318 plus 1.28. This is going to be a plus. This is going to be a 2. So now we've got the equation in there. I can hit solve. So like I said, the negative value here, that's telling us that if the ball was traveling the opposite direction, it would end up about 1.5 feet behind home plate. In the other direction, that 404, that's the actual distance the ball traveled if it had been hit into an empty field. The next question that you need to ask here is, how do I know that at a distance of 220 feet, it reached a maximum height of 130 feet? Well, you have to use cameras to actually take that particular measurement. With a lot of the systems that are out there now, they can do that fairly accurately and fairly quickly. But does that actually sound like a really good use of a quadratic equation, other than trying to figure out what is the height of a telephone pole? Another thing we can do with these quadratics, which is actually a useful application, is we can look at basically demand versus production versus profit, production versus units sold, or something like that. So over here, I'm going to say that the y-axis is money, and then the x-axis is the number produced. When we look at an equation like this, the y-intercept down here, so if we're thinking of this in terms of y equals ax squared plus bx plus c, this is just going to be the c value here. This could be startup cost or a fixed cost. Because this is a quadratic, we're going to find, I'm going to call it x1. That's where you're going to start making money. So that's well, you need to make at least that many of the product before you start making money. And depending on the graph, that could also be called the break-even point. Out here, I'm going to call this x2. It's where you stop making money. And if you think about it, this could be, say, a demand graph for any type of product that you'd want. If you think about, say, like Apple iPhones, they're now on what version? If you had a whole bunch of Apple 1 or Apple 2, do you think they'd sell that many of them? Do you think there's much of a demand for outdated electronics? And that's basically what this is saying. If you make too many of them, after a while, you're going to lose money, because basically you have to discount it so much in order to sell it, or take a write-off, and then you lose a whole bunch of money because you spent money to produce them. Now you have to destroy them somehow. And what's going to happen here is something called the apex. That's going to be the maximum amount of money you make, or the maximum profit that you can make. For a problem that I gave my students in a different class, the equation is based on an electric company is trying to figure out how much electricity to make at one of its generators. So the number produced is millions of kilowatt hours. And then The y-axis is the amount of profit that's going to be made at based on that. The equation that they were using is y equals -6x squared plus 2,700x minus 63,700. So that's 63,700. Again, we can think of that as a startup cost or a fixed cost. So that might be how much it costs to keep all the employees, or you pay all your different employees that are going to be working at this power plant in a given hour. Once we've figured that out, we can then go in and figure out what is the X value where they start making money, what is the X value where they stop making money. We can also figure out what this apex is. And the apex, it's going to be in an XY format. The X here is -b divided by 2a. Then the Y here is Y at whatever this value happens to be. So what is the X value at the apex based on this equation? -b, so -2,700 divided by 2 times A. A is -6. So this is going to be -2,700 divided by -12. The negatives will cancel out. Damn it. Should just get rid of that so I don't keep clicking on it like an idiot. So again, we've got our equation. We can figure this stuff out. But for right now, I'm going to figure out what is the X value for the apex. So 2,700 divided by 12. So my X value here is going to be 225. So that's telling the company that they should produce 225 million kilowatt hours of electricity. We can then plug that into the equation that we have to figure out how much money they're going to make at X equals 225. So we have -6 times 225 squared plus 2,700 times 225 minus 63,700. So the company can expect to make $240,050 in profit, maximum profit, when they're running this electric plant. The other thing that we need to know is, at least based on that particular equation, where do they start to make money? Where do they stop making money? So again, I can go to the apps, come down to Police Molt 2. I want the polynomial root finder, second degree. So here I've got -6 times x squared plus 2,700, and then minus 63,700. Now that I've got all that, I want to solve it. And this is telling us that x1 is about 25, x2 is about 425. So on certain days, like if it's a really, really cold or if it's really, really hot out, there's probably going to be extra demand for electricity. This is saying that if they produce more than 425 million kilowatt hours of electricity, they're actually going to be losing money. So they want to try to stay as far away from that as possible. On days when it's say 60-ish or 70-ish, you're not really turning on the air, you're not really turning on the heat all that much. So electricity demands are going to be down. This is saying if they use or if they need to produce less than say 25 million kilowatt hours or whatever the units were, they shouldn't even have the plant running at that point. And as long as they keep it between those two values, they will actually be making money and they will make the most amount of money at 225 million kilowatt hours or whatever the units happen to be again. So for those of you that are going to be getting into business, this is stuff that you do in economics quite often. Try to figure out what is the maximum amount of money that you should be making. And I will say, so how many of you are actually business majors or thinking about business majors? Okay, so when it comes to the economics, the you have to watch what the equation is actually saying here. If we're looking at uh, money in terms of profit, and we're trying to figure out how many we should make, you want to figure out whatever the apex is. If we're talking about instead of profit, just how much money you make, you're actually going to want to go with the X2 value. Because if you make less than whatever X2 happens to be, there's still the ability to make a little bit more money. So you should produce that one extra item or whatever it is. So depending on how the equation is set up, you're either going to be looking for the apex or X2 in a lot of your, or when you're trying to make a lot of different business decisions. A lot of the applications in here are that they come up with are like we're looking at here. Try to find the length and the width of a tablecloth based on these really stupid values. I don't think we need to bother with that sort of stuff. Looking at something like this, it says a firework is a shot upwards with initial velocity 130 feet per second. How many seconds will it take to reach a height of 260 feet? Then it says round to the nearest tenth of a second. And you can see 130 feet is the initial velocity. So this V0 in the equation is going to be 130. Height is going to be 260, which is where all these numbers come from. And then you can see that they basically pull everything off to one side. And then they ended up multiplying everything by a -1 to get the values that are on here. Plug everything into your quadratic formula. And with this one, the 200, or what this is actually telling us, is that the 260 feet, that's not how high the firework actually went. Uh, the 3.6 seconds that it shows on there, it was still traveling upwards at 260 feet. Went higher than that, then exploded, then fell back down again, and the second time it hit 260 feet at 4.6 seconds. So if we're trying to graph or get an idea of what the graph of this looks like, or what they're actually trying to do, is, again, we've got something like that. 260 feet is there, and we're looking at time, and basically it goes up and then it comes back down again. This is like the 3.6, and this is the 4.2 or whatever is showing on there. If we also know that at a time 0, it's actually on the ground, which makes sense, right? Because before you launch a firework, it's going to be on the ground, or at least hopefully anyway. We know at we've now got points 0, 0, and then 3. All right, so it should actually be 3.6, 260, and then 4.6, 260. We can go back, figure out what the quadratic equation is, or we can use this one. So we can also go back and try to answer the question, how high does this firework actually go? Or how long does it, sorry, I should say, how long does it take for this firework to get to its highest point? So that apex thing. So the equation for the apex is negative b divided by 2a. Negative 130 is b. So negative 130 is going to be a positive 130 divided by 2 times 16. So we can try doing that in the calculator. So we've got 130 divided by 32, since it's 2 times 16. So it takes a little over 4 seconds to actually reach its highest point. We can take that, plug it back into the equation that we have originally here, and we can actually figure out how high it traveled. So again, a couple other questions that do the same thing. And how many of you remember these problems from earlier? About traveling upstream, the engine is pushing the boat at a certain mile or certain speed, but if it's going upstream versus downstream, figure out what the speed of the boat is and figure out what the speed of the stream is. That's literally this whole thing right here. I think we've done a couple different problems like this, right? Boat travels upstream, boat travels downstream. The difference is here, they're actually telling you the speed, in this case, the speed of the plane or the speed of the boat. You just have to figure out what the speed of, in this case, the jet stream is, or in the case of the boat, what the speed of the river is. So it makes it a lot easier. When you go through, you can see all the different steps that they have there. What they're actually doing here is they've taken the equation velocity equals distance divided by time, rearranging it to get time equals distance divided by speed. The rate here, according to what they're saying here, is 450 miles an hour plus the jet stream, and then going back 450 miles an hour minus the jet stream. And you're also told that the distance is 2,000 miles. So that's where this whole thing comes in. And then you have the time getting there plus the time getting back. is equal to 9. We have a really ugly fraction. And when you get done collecting all the like terms and everything else, it eventually turns into a quadratic. You can then solve that quadratic and figure out what the speed of the jet stream is. So if we're going to try to do that, and I think this was another type of problem that was on a previous exam. If one person can do the job in 8 hours, another person can do the job in 12 hours. How long does it take the two of them to do the job if they work together? Do you remember that type of problem? That's exactly what this problem is. The difference is, you know the time that they can do it together, and you know that one is a little bit slower than the other. But it's the exact same math that we did before. So it's 1 over T1 plus 1 over T2 equals 1 over T total. And then because we've got all these fractions here, do we like fractions? Absolutely not. So what do we have to do? Multiply everything by the largest denominator, then the next largest, then the next largest, and so on. Eventually you get the quadratic that they're showing here, and then you can figure out how long it takes for all these things to work. So if we're looking at like a 9.82, so party with a hot tub. Anyone else in for that? Uh, if she uses one hose, it'll take 3 hours more than if she only uses the green hose. If she uses both hoses together, the hot tub fills in 2 hours. How long does it take for each of those to fill the hot tub? And then what's the realistic question that we have to ask here? If you can use two different hoses, why wouldn't you? Right? Or am I just making things up again? Or what's the other question that we really need to ask here? Why do we care how long it takes one of these things to fill up the hot tub in the first place? But that's part of the problem here. So again, and I know that you can't see what I'm writing just yet. But it's 1 over T1 plus 1 over T2 equals 1 over T total. This is saying that if she uses both of them together, it takes 2 hours. So this is telling me that T total is equal to 2. Looking at what it says, if she only uses a red hose, it takes 3 hours more than if she only uses a green hose. So time 1, call it, or say this is for the red hose, and then T2 for the green hose. Because it relates everything to the speed of the green hose, T2 is just going to be T2. And again, I know that you can't see anything that I'm writing down yet. I'll show you in a moment. And it says the red hose, it takes 3 hours more than if she only used the green hose. So T2 plus 3 is equal to T1. Now we're like almost ready to do a thing. So we've got 1 over T2 plus 3 plus 1 over T2 equals 1 over 2. Now, if you remember, one of the things I said about these types of problems, because we've got the fraction over here, we we can turn this thing into a fraction with a common denominator, then just flip the whole thing over, make it easier on ourselves if we want to. So let's do two different ways here. Using the method from the book and using the idea that I've been talking about since the beginning of class. Do we like fractions? Yes or no? No, we don't like fractions. So what do? We multiply by the biggest denominator, see what happens, then the next biggest, see what happens, then the next biggest. I'm going to just come out and say it right now. Looking at what we have here, uh, multiplying by any one of these is not going to cancel out something in a denominator. So it will be multiplying everything and by t2 plus 3 times t2 times 2. So t2 plus 3 times t2 times 2. Out here, t2 plus 3 is going to cancel out with the t2 plus 3, and we multiply it by 1. So this is going to become t2 times 2. Over here, got t2 in the denominator. So this is going to be t plus 3 times 2. And then this whole thing is going to be equal to t2 plus 3 times t2. This 2 will cancel out with that one. Collect, uh, distribute, and then collect like terms. We've got 2 t2 plus 2 t2 plus 6 equals t2 squared plus 3 t2. 2t2 plus 2t2 is 4. Got a 3 over here. So minus 4 t2 minus 6 minus 4 t2 minus 6. Eventually we get 0 equals t2 squared minus t2 minus 6. Factor that. If you see how it factors instantly, awesome. If you don't, you can use Poly-Smolt 2 or the quadratic equation. So we get t2 minus 3, then t2 plus 2. So this is telling us t2 equals either 3 or negative 2. Since you can't fill it in negative time, that's telling us that t2 is equal to 3. Plug that in here. T1 is going to be equal to 6. And we're done. Or we can come up with the reduced weight equation here. Which would be T2 plus T2 plus 3 over T2 times T2, or T2 times the quantity T2 plus 3. That will equal 1/2. So 2 T2 plus 3 over T2 squared plus 3T equals 1/2. Flip it over. Multiply both sides by that. And eventually, when you collect all the like terms, you end up getting the same thing. Trying to do it that way usually takes a couple less steps. Another way of trying to get there. And with 9.6, so what's the objective here? Graphing. We've got calculators. We can graph it that way, right? So this is going to be a lot of boring stuff. So one of the things that they're trying to get you to do here is trying to plot the points based on f of x equals x squared. For any time where it says like basically graph or plot whatever, the big idea that you're supposed to have is you start choosing values of x, plug them into the equation, you get a value for y. We already know how to do this with the graphing calculator, right? We can go to stat, we can go to edit, and we can call L1 our x values. What values do we want to use here? -3, say -2, -1, 0, 1, 2, 3, whatever it happens to be. Do we, depending on the equation we're dealing with, do we really care what values we have the calculator calculate? Not really. If we're given a like some graph paper to graph on, do we care what values of x we put in there? Um, so again, just with graphing in general, if you're given an equation, like say y equals 5x plus 3, uh, you can just start plugging in pretty much any value of x that you want. What values of x do you really want to use here? The easy values, right? If you're going to be using a graphing calculator, does it really matter? Not so much. Why is that? Uh, we've got an integer, we've got an integer. When you plug in an integer there, you're going to get an integer over here. So easy to graph. On the other hand, if we had something like that, what are the values of x that we want to deal with? Again, we want to start off with our favoriteest value of x. And then we want to use multiples of the denominator here. So we could do -5, -10, 5, and 10. Why are we doing multiples of the denominator? So things cancel out. Because you plug in a 0 here, 0 times 1/5 is 0. 0 plus 3 is 3. Plug in a -5. -5 divided by 5, -1. -1 plus 3 is 2. -10 divided by 5 is -2. -2 plus 3, 1. 5 divided by 5, 1. 1 plus 3 is 4. 10 divided by 5 is 2. 2 plus 3 is 5. And those are really nice numbers to graph there, aren't they? So again, with the graphing calculator, plug everything in. The equation that's in the book is just x squared. We can do a lot better than that if we wanted to. Again, highlight L2. we can do L1. So if we want this to be squared, so let's say we've got L1 squared plus 5 times, so x squared plus 5 times x plus 6. And we just let the calculator do all the work for us. Why do we need to make it harder on ourselves than we need to? So a lot of this is going to be based on stuff like that. So again, how do you determine what values to put in? Well, there you go. When you're graphing these, if you see the negative value out in front of x squared, it's going to open face down, so it's going to be like a frowny face. If it's positive out in front, it's going to look like that, so it's going to be a smiley face, just to make it easier. This is open up, and so this is open up, this is open down, all right? Again, and you can see what it's talking about right there. So just looking at where it says here, determine whether each parabola opens upward or downward. If the thing in front of the x squared is negative, it's down. If it's positive, it's up. So what's the value for the x squared term here in front of the x squared term? Negative or positive? Negative. Negative means it's down. What's the value out in front of the x squared term in b? Positive or negative? So it's smiling. It's easy enough, right? And if you get confused by that, what do? Graph it, right? Hopefully by now we know that one, we should always be graphing it before we math it, right? And once you've graphed it, you get an idea about a whole bunch of different things that are going to be going on here. So again, here, that's positive, so it opens up. That's negative, so it opens down. Yay, we're done with that. Axis of symmetry and vertex of a parabola. So we were just talking about this type of thing. For the company that's producing electricity, uh, what is the axis of symmetry? For them, it's how much electricity do they produce to get the maximum profit on a particular day. The vertex is going to be that X and Y combination that said at 225 million kilowatts or whatever it is, they will make $240,050 maximum profit. For the baseball thing, that was the highest point that it reached. And so if we're talking about if anyone's watches football or whatever, uh, what's the hang time? How long does it take from when the punter kicks it from when he kicks it to when it comes into whatever the receiver's hands are to try to run it down the field or do whatever? This we can figure out we can figure out how high they actually kicked it. So just looking at this, the axis of symmetry, so this is that x value when x equals negative b divided by 2a. Here b is -6. Negative times a negative is a positive. Positive number out here means it's a smiley face, so it opens upward. -6 divided by, or sorry, -6 divided by 2 times A, so 2 times 3. Where's the vertex going to be here? So you can see what's going on down here. Comes out as x equals 1. So the axis of symmetry here, it's just x equals 1. What is the vertex? We now have to take that x equals 1, plug it into our initial equation, and we get, in this case, -1. So if we're looking at 988, we've got y equals 2x squared minus 4x minus 3. We want to figure out what x is equal to. We need to figure out what y is equal to. So let's try to do that. So the axis of symmetry is -b divided by 2a. Looking at the equation here, again, this is positive, so it's going to be something like that, which is telling us that the value we're going to find is actually going to be a minimum. Plugging in the values that we have, -4 divided by 2 times 2, negative times a negative is a positive, so we get 4 divided by 4. That's just going to be equal to 1. Plug that into our equation here. So 2 times 1 squared minus 4 times 1 minus 3. 1 squared is 1. So this is going to be 2 minus 4 minus 3. So -4 minus 3, -7. -7 plus 2 is -5. So this point right here is at 1, -5. So not too horrific yet. On this one, it's talking about find the intercepts of a parabola. So keeping in mind what the intercepts are, the y-intercept is just what does y equal when x equals 0. Easy enough. Plug in x equals 0, whatever's left over, whatever you get, that's the y-intercept. That's easy math, right? So if I ask you here, what's the y-intercept? Well, you have to plug in x equals 0, 0, 0, 3. Whatever the last number is. Just grab it, right? Now, the x-intercepts, these are the value of x when y equals 0. What's another way of saying that? What value do we get when we factor this equation, right? So doing the exact same math you've been doing for pretty much this entire chapter and a considerable amount of previous chapters. You get a totally new name here. So for this one, if we want to figure out what are the x-intercepts of the parabola, it's negative here, so we know that if we're going to graph this, it's going to be a frowny face. Looking at everything else, plug in the values into the quadratic equation to figure out the x-intercepts, which again is what value of x do you get when y is 0. What's the y-intercept for that? 3. Anyone else bored with this stuff yet? Is anyone bored with this stuff like 20 minutes ago? So a lot of what's going on in here is again, find the intercepts. Y-intercept x equals 0. So what's the y-intercept for this one? -8. What's the y-intercept for the other one? -12. Toughest math you've ever done, right? What are the x-intercepts? I'll factor it. Okay. And then you see all of this stuff. So I will say, like what we've got here, we've already kind of talked about it, even though we're now talking about it here. This is just saying everything that goes under the square root in your if you're trying to factor things. If that ends up being greater than 0, you have two real solutions. If they exactly equal 0, you have one solution. But with quadratics, you're supposed to have two values of x. So you write the same number down twice. So x minus 2, x minus or times the quantity x minus 2, something like that. If it's negative under the root, you have complex values. We already know that, right? And I've already talked with you all. If you graph it, and you end up with something that doesn't go through the x-axis, it's going to be complex variables, complex numbers. Which means all of this is what? Getting very boring and very repetitive? Yes or no? So here are more things here. Graph f of x based on its properties. Some of the stuff is grab a bunch of values of x, plug it into your calculator, plug it into the equation, see if it looks like, plug it into the graphing feature of your calculator, graph the stupid thing. You can also look at it and try to figure out what is the axis of symmetry going to be, what is the where's the vertex going to be at. So again, if we want the vertex, negative b divided by 2 times a. So -2 divided by 2 times 1. 2 times 1 is 2, -2 divided by 2 is -1. Plug that into your equation and you have your inflection point. You have your apex. Because the a values in both of these are positive, these are smiley faces, which means the apex is the minimum that we're going to be looking for. If that's negative, that's going to be a maximum. Okay. And then there's all this stuff trying to graph everything. Anyone else tired about with this? All right. So since I wrote that out poorly. Those are the two equations. Number one is graph it and tell me, does it face up or face down? If you remember what I said about facing up or facing down, you can look at the value that's out in front. There you go. A line of symmetry. So what is the X value where we have the apex at? What is the vertex, which is where you take that X value, you plug it back into your equation. Then tell me, is that a minimum or a maximum? And then this is y-intercept. So that means what? Y at x equals 0. X-intercept. When you're done, bring it on up. Don't you wish every day went this quickly? So with this, there are going to be multiple. There's the graph for equation A and B, the line of symmetry for A and B, the vertex for A and B, the intercepts for A and B. So you're doing basically the same math twice.